Hello, everybody. Can you hear me?
Yes, Professor Gutierrez.
Yes,
Thank
good
you.
morning.
Okay, so we're continuing here with Module 6. And again, please make sure your video is enabled. Thanks. Okay, so we were on to predicting reactions with acids and bases. And the first thing we need to do is define what we mean by an acid and what we mean by a base. Now, acids tend to be things that have, well, they are things that form H plus when you put them in water. And those things usually have an H out the front. So they can have an H out the front, like HCl, H2SO4, H3PO4 are all examples of acids. And we know this because the H being out the front means it's a cation, so that makes it H plus. But there are other situations where the H can also be in the middle of the compound. For example, in NaHSO4, CaHCO32 are both examples where H plus is also possible to form as well. Bases generally have OH minus. Well, they form OH minus when you put them in water, and they'll have an OH in them like NaOH or CaOH2. So those are usually pretty easy to figure out which is which. And as far as acids and bases go, when you add them together, they tend to form salt and water. Now, when I say salt, I don't just mean sodium chloride. Yeah, sodium chloride is called salt, but it is in general a salt. A salt is something that contains a positive and negatively charged species. It's really just a binary compound is all it is. And the H2O comes from the H plus and the OH minus from the acid and the base coming together to form water. Does anybody have any questions so far? So the focus now is on what do we do when we're given an acid and a base, and how do we determine what compound is formed, and also how do we balance the reaction that results from it. This is usually something that gives a lot of people trouble, but once you get the idea behind it, it's actually not as bad as it seems. So I'm going to give you an example here, NaOH plus H2SO4. So we're interested in figuring out what the products are and then what we're going to do to balance it. What we should do to start is write out what these things are with the charges on them. So we know that NaOH is the base because it's got the OH. If we were to write it out, it's Na plus and OH minus, because OH is always negative. It means the Na must be plus as well. H2SO4 would look like two H's and an SO4. Now the charge on SO4 is -2, and we know this because we can get that off the polyatomic ion sheet. We also know that H is going to be 1 plus, so if there's two of those, that must be -2 as well. So there's lots of different reasons for why we know that H is going to be 2 H pluses and then the SO4 is going to be -2. Does anybody have any questions so far? Well, we know we're going to get H2O out of this, and that's going to be from the combination of H plus and OH minus. Now you might be wondering, and this is the big question that students always have, is they say, well, what do we do with this H plus down here? Why don't we form H3O or something like that? I mean, in order to balance this out. Well, because that's not our first priority. Our first priority is to figure out what compounds we're getting, and then we balance the reaction at the very end. We know that the other things we're getting are going to be from the combination of the Na plus and the SO42 minus. So we're getting Na plus and SO42 minus. They're going to join together here. And the compound that we get from that, actually I'm going to rewrite this down here. Is going to be Na2SO4. And the thing I'm trying to do here is I'm trying to say, well, I've got one Na plus SO42 minus, Na1 plus. How many do I need in order to make that balance out? Well, I need two NAs to do that. And so, often the question is at this point for students is, well, how can you just grab a sodium out of thin air and put it in there when you've only got one sodium on the other side? Again, it's for the same reason I'm only using one H plus and one OH minus from over here. It's because my first priority is not to balance the reaction. My first priority is to figure out what compounds I'm getting, and those compounds will always even out for their positive and negative charges. That's always the first priority. After I've done that, then I can go ahead and balance the reaction. Having two sodiums over here, I can put a 2 in front of the NaOH, and then I need a 2 in front of the water here, and that will balance out my hydrogens and oxygens. So the SO4 already balances. We've got two oxygens, there's two oxygens. We've got two hydrogens here and two hydrogens here. That's a total of 4 hydrogens, which means it's now balanced. So that would be the final balanced equation we would need if we were dealing with sodium hydroxide and sulfuric acid. All right, I'm going to stop here for a second. Does anybody have any questions? Usually people do. I mean, it's not really an intuitive thing to say, well, I've got one Na plus and SO42 minus. Well, how do I negotiate that? How do I make that a compound that I can work with? Well, you have to first of all figure out the positives and negatives. Does anybody have any questions at all?
How did you know to put the OH minus and the H plus together?
Okay, the whole nature of this kind of reaction, and we're dealing with these pretty much in the next part as well, is that it's called a double displacement, which means that the cation from one side is going to join with the anion of the other side. So you think about it like this kind of situation: AB plus CD gives, let's see, this will be CB and AD. So think of it like two couples dancing and they switch partners. Male and female, and then they switch partners with the other male going with the other female. Is that clear, Karina?
Yeah, that makes sense. I'd forgotten about the ABCD thing, but that makes sense now. Thank you.
Yeah, the reason it's CB is because the H is positive and we always put the positive ones first. Okay, any other questions about this so far? Okay, the other one, which has the acid and the base, but now the acid has the H in the middle. You might be wondering, well, how would you know it was an acid-base reaction? Well, what's going to happen is on the test, I'm actually going to tell you that it's an acid-base reaction. So you'll know that something's an acid and something's a base, and that'll be a good clue for you to know where you're going to go from here. So if you've got CaHCO3 2 plus CaOH2, Again, we can draw pictures of what this looks like. And again, we know that Ca is 2 plus because it's in group 2, or you can say there's 2 OHs with it, so they're negatively charged, which means that Ca must be positive 2. So the H comes out here as H plus, and the H plus is what joins with the OH minus. And that's what forms the water. Does anybody have any questions so far? So one question you might have is, well, how did I know to take the H plus out? Right? I mean, it's a fair question. The thing is that I'm telling you, I would tell you that it's an acid-base reaction. So if you know that one of them has OH minuses, you've got to get H plus from somewhere. The only place you can get H plus from is from the middle of that compound. So that's how we're getting the water. Now the rest of it is going to then be the Ca2 plus, and whatever you get once you've taken the H plus away, which would be CO3 2 minus. And again, we know the charge on the CO3 from the polyatomic ion sheet. So the H so the H is coming from the HCO3, and then the anion becomes CO3 negative 2. And the final thing that we're going to get here, squeeze it in down here, I don't want to erase any of this. So I'll go ahead and rewrite this. CaHCO3 2 plus CaOH2 and that becomes CaCO3 plus H2O. The order of those doesn't matter. You can put the H2O first or the CaCO3. Now we need to balance that. We've got 2 calciums on the right, so we need a 2 over here, which also balances the CO3s, and it looks like we need 2 oxygens from the 2 OHs, so 2 H2O is what we'd have there, and then that would be balanced. Does anybody have any questions? Anybody have any questions? Well, the main question you should have is right now is, how's this going to look when you test it on it, right? Usually that's the question I often get. So let's go take a look at how that would look. Test 1. So let's look at the sample module 1 to 6 test. And you can see the kinds of questions you're going to be asked about this. Okay, so we're into module 6. So you can see it's all done by module here, module 5 naming. And we're into module 6 here. So the first question you'll see will be a balancing type question, and we talked about these earlier, and sum of coefficients. One thing we haven't looked at, and we'll get to this in a second, is the balancing of hydrocarbon combustion problems. So here is the acid-base question. So there's actually going to be, well, it's really just one kind of question you'll have to answer. You actually won't even have to balance the reaction at the end. all we're really interested in is knowing what compound we're getting, what compound A that we're getting along with the water. Remember, you're told here it's an acid-base reaction. The other clue is that you're getting water as a product. That's also helping you out here as well. Hang on, let's close that. Let's take a look at how you would do this. So what I would do is this: I'd do Al, and I would split it up into its positive and negative components. I know it's got 3 OH negatives, so that would mean that Al is going to be 3 plus. And then we've got H and F, and that would be H plus and F minus. Does anybody have any questions about where I'm getting any of those charges from? The OH minus and the H plus are forming water. And that leaves me with the compound A, which is going to be the combination of Al's 3 plus and F minus, which would have to be AlF3. And that's all I'm looking for. That's it. That's the answer. Does anybody have any questions?
And so I do. So
yes, you, Sarah.
For when you're going to choose the actual answer on the test, we would add AlF3 and then the minus sign on the top with it. I mean, there's no charge with it.
No, that's the whole point. You need to come up with something that's charge neutral. In other words, you know, the positives and negatives have to balance each other out.
Okay, so because I think I kind of mixed that question up, because in the assignment that I'm doing with it, it's just asking for one of the charges, and it gives me a whole bunch of drop down lists of different of that element with the different sub numbers there, and then the charge. Would I put in the element with the charge itself, or would it put the element and how many of those it is to complete? Like, let's say it's Al 3 plus F minus, I would put Al 3 plus, and then the other one would be F3 minus as the second part of the answer.
No, because it's if you're talking about the assignment,
yeah,
the assignment is stating, and it states very clearly, you need single anions and cations.
Okay, so I wouldn't add the 3. I would just put F minus.
You just put F minus.
Oh, okay.
Now, the reason for that, Sarah, is because it's just exactly like what we're doing here. Anything we're forming is always based on single anions and cations. You'll notice that when I formed water, for example, I took one OH minus and one H plus. I didn't take all 3 OH minuses. Do you see what I'm saying?
Mm-hmm.
And over here, it's one Al3 plus and one F minus to form the AlF3 compound. In this case, I'm looking for the AlF3 answer.
The whole answer, that's when we put in the number with it of how many fluorines we need.
Yeah, and it's always going to be charge neutral as well.
Okay, perfect. I get it now.
Okay. Now, for the assignment, that's a different story, because you're looking for the actual single anions that are making up the compound. And if you were asked that question about this, these would be the single anions and cations, the Al3 plus and the F minus. Okay?
Okay, perfect.
No worries. All right, any other questions? Any other questions? Okay. So that's pretty much all you really have to do, and I don't think it's that bad, really. Does anybody have any questions? I guess, you know, I'll keep on answering any questions anybody has if they're concerned about this.
For the AlF3, sorry, you can go.
No, it's fine. Mine's more of a no.
You go first, please. Karina, you actually jumped in first, so.
Karina? For the AlF3, the F got the 3 on the bottom because the Al had the 3 plus charge, right?
Well, so the question I was asking is how many of each do I need to make this compound neutral? And because F is -1, I need 3 of them in order to make it balance out.
Okay.
So the ALF3, once I drew it, would look like this. And it would be a nice balanced compound. This is always our aim, Karina, is to have these charges matching. So
yeah, that makes sense.
Yeah, just understand, it's not like I'm just pulling the F's out of thin air. Okay, the F's are being brought into the picture because I need to know what the compound looks like before I balance the reaction.
Yeah, that makes sense. Thank you.
Okay. Joseph?
My question was, so the two that we're dealing with in this class are acid and base and combustion, you said? Okay, not gone over combustion yet.
We haven't gone over combustion. The other thing we haven't gone over yet is the double displacement as well. That's the other one we're going to deal with. We're also going to deal with some single displacement reactions too, as well as some combustion reactions. Sorry, combustion, not combustion, decomposition.
Okay, thank you.
All right, any other questions? Okay. So remember, if this is a question that you've had trouble with in the past, one thing you can do is you can just take this test, this sample test, and just do that question 26. Just do that question and make sure you're getting the right answer each time. And when you're consistently getting the right answer, I think that's when you'll know that you pretty much understand what you're doing. Does anybody have any questions? Okay. All right, let's look at the next one. Okay, so this is predicting reactions for combustion of hydrocarbons. So hydrocarbons, as you might have guessed, are compounds that contain, well, hydrogen and carbon. That's why they're called hydrocarbons. So the general formula for a hydrocarbon is going to be C6h6. The Y number will always be an even number. The X number can be odd or even. And that's going to matter, well, that kind of won't matter that much, I guess, but there are going to be things that matter about odds and evens that are going to be helpful to you when you are determining how to balance a hydrocarbon reaction. Now, the product of a hydrocarbon combustion process is always CO2 and H2O. And if you think about it, as human beings, that's exactly what we're doing as well. We take in food as fuel, generally in the form of things that can be broken down into glucose. And glucose is just carbons, hydrogens, and oxygens. And then those get metabolized, and we end up breathing out CO2 and H2O. So one other thing here I'll just throw in here. People wonder, you know, if you're trying to lose weight, how do you actually lose weight? Well, a lot of people think it's through the processes of excretion or just bodily functions such as that. But really, the main way that we lose weight is through combustion of food and turning that food, which contains carbon in it, into CO2, which we breathe out. So when we lose weight, we're actually losing weight because we're breathing out more CO2. So that's kind of interesting. You can look that up if you'd like. But let's talk about some examples of these hydrocarbon combustion problems. We've got C4H6 Plus O2. The products of these reactions are always CO2 and H2O. When we're balancing, the first thing we do here is we balance the carbon. So it'd be 4 carbons out in front here. And then we've got 8 hydrogens, so I put 4 out in front of the H2O like that. Does anybody have any questions so far? When balancing the oxygen, we need to be careful here because we've got oxygen in two places. We've got 4 times 2 is 8 plus 4 is 12. So that would be 12O on this side, which means I also need 12 oxygens on this side, which means I need to put a 6 in front of the O2, and that would be balanced. The sum of coefficients would be 1 plus 6 plus 4 plus 4, which is 15. Does anybody have any questions?
Yeah, I was wondering why is it as a product why is it always CO2 and H2O?
Because if you've got, and generally we do, we have enough oxygen to do this, but if you're burning a hydrocarbon, the products we get are the most stable products that we could possibly get from that reaction, and CO2 and water are the most stable products that we can get. So it's always CO2 and H2O. If you have insufficient oxygen, it's possible to get carbon monoxide, CO, formed, but that would only happen if there was insufficient oxygen to react with the C4H8.
Okay, thank you.
Okay, Charles. All right, let's look at the other one, C6H6 Plus O2. And again, it'll be CO2 and H2O. This is not something you have to memorize, by the way. In the test, I actually tell you what the products are. So we put a 6 in front of the CO2 to balance the carbon. And then we've got 6H here, so I need a 3 in front of the H2O over here. Does anybody have any questions so far? Now, if we look at the oxygens, we've got 6 times 2 is 12, plus 3 is 15. 15 oxygens. 15 divided by 2 O2 is what we're going to get on the oxygen. So when the reason it's 15 over 2 is because if you got 15 over 2, it's like 7.5. And 7.5 times 2 is 15. But what does 7.5 O2s look like? Well, it would look like this. So these are oxygen O2 atoms, and then 7.5 would be 7 O2s and then 1 oxygen left over. And that's in essence what 7.5 O2s look like. But we don't like dealing with half molecules here or fractions. So what we do is we take the whole thing and we multiply it by 2. And then when we do that, we end up with 2 C6H6 plus 15 O2s gives 12 CO2s plus 6 H2O. And when you balance that out, you'll see we've got the 12 carbons on each side. We've got 2 times 6 is 12 hydrogens on each side, 6 times 2 over here. Over here we've got 15 times O2, which is going to be 30 oxygens. Here we've got 12 times 2 is 24 plus 6 is 30. So it does balance out. But you'll notice that for this one, we had to multiply by 2 and the other one we didn't. Does anybody have any questions so far? There is a pattern, though, to knowing when we have to do the multiplication by 2 and when we don't. And that pattern is as follows. What you do is you look at the number of hydrogens. And you ask yourself, if I divide that by 2, do I get an odd number or an even number? So when we look at 8 and we divide it by 2, we get 4, which is even. In this instance, we don't need to multiply by 2 at the end to get the balanced equation. If we take the other one, though, we've got 6. 6 divided by 2 is 3. 3 is odd, which means that we will have to multiply by 2 at the end. Does anybody have any questions? All right, let's look at some of the examples here. I'd like you to tell me, C7H8, do you think you're going to have to multiply that by 2 or not? Any question? Any thoughts?
No.
No, you don't have to, because 8 divided by 2 is 4. What about C5H12?
No.
No, because 12 divided by 2 is 6. C6H8 is like the other one. All right. What about C7H10?
Yes.
Yes, 10 divided by 2 is 5. That's odd. C6H6 we already dealt with. What about C6H14?
Yes.
Yes, 14 divided by 2 is 7. All right, any questions? Okay. All right, now we're going to look at predicting and balancing double replacement reactions. This is where also we talk about net ionic and full ionic equations. Again, things that people don't like a great deal. Oops, sorry about that. Didn't mean to do that. Okay. So I've got the same kind of notation as I had earlier. We've got AX plus BY. It's kind of like the AB plus CD. AY, so the combination of the A and the Y and the B and the X. So the outsides and the insides are what we get joining together. A and B can be a metal or even possibly H. And X and Y are single element anions or polyatomic anions. So when these two add together, what usually happens is that either AY or BX can become a precipitate or a solid, whereas we're starting out here with a kind of an aqueous kind of equation. So let me show you something. I'm going to go to YouTube here. Actually, I'll go to, I won't go here. Let's look at an example. And we'll go we'll go K, no, yeah, PB. Here we go. All right, let me change the share on this so you can. Actually, I'm not even going to bother with the sound. I'll just speak over it. All right, so what we're doing is we're taking potassium iodide and lead nitrate, and we're going to put them together. And it's actually lead 2 nitrate. And if you look at these solutions, let's have a look at them. There we go. You'll notice that they're both, well, they will be both clear colorless liquids. What he's doing here is he's putting lead nitrate into a test tube. He's going to add water to it. And the potassium iodide is also a solid, but he's going to add water to that as well. All right. So these are the 2 solutions here, and that really should be more colorless, clear and colorless. But what happens is that since they're both aqueous solutions and we add them together, what's going to happen is that we are going to end up getting, you'll see in a second, he's adding them together, you get this yellow solid precipitate. So if you let that sit for a bit, it'll, let's see, I'll wait and see if it, you can actually look at it. You can see that, hang on, you can see that there's a bunch of solid on the bottom, and And that's the precipitate that's formed. And we need to be able to figure out what that precipitate is as well. So that's an example of what we're doing. Now, when we're doing the actual balancing and predicting, we need to first of all do that, balance and predict it. Then we need to write a full ionic equation and a net ionic equation that comes from that. All right, so let's see how we navigate that process. So I've got an example here, PbNO3 plus Na3PO4. And what we're trying to determine here is what the products are first. So the first thing we do is we draw pictures of what we're dealing with. So PbNO3 will have two NO3s which have a -1 charge, and that makes the Pb2 plus. And then we have three NAs and the PO4. PO4 will be -3 and the NAs will be 1 plus. Does anybody have any questions so far about where these charges are coming from? Especially the charge on the lead, because the lead is one of those that can vary with the charge. It can be 2 plus or 4 plus. It's 2 plus here because we've got two nitrates in the compound. Anybody have any questions? All right, so what are we going to join together? Well, we're going to join together the Pb and the PO4, the Pb2 plus and the PO43 minus. And we're also going to be joining together one Na plus and one NO3 minus. And again, the question that people often have is, well, why don't I use all of them? Well, I'm just choosing one of each because I need to figure out what compound we're going to get from those two anions. So when I do that and I rewrite it, we'll get PbNO3 plus Na3PO4. And that gives Pb, and I need to see what combination of these I'm going to get. It's going to be Pb3 PO4 2. That's to make those charges even out. And then NaNO3, Na plus NO3 minus would just be NaNO3. Okay. I'm going to stop there for a second. Does anybody have any questions about what I've done so far?
How'd you separate the NO and the Na again?
I'm not understanding your question, Sarah. I'm sorry.
Well, just, to moving it over to the reactant side. So instead of like, how'd you move it to where it's Pb3 PO4 plus NaNO3? Like, I just got lost in that process.
Okay, so do you see how it's that Ax plus By business that we were looking at earlier?
Uh-huh.
So we get A combining with Y, and X combines with B. Or I should say B combines with X, I should say.
Okay.
So insides and outsides. One cation combines with the anion of the other.
Okay.
You sound skeptical.
I'll see if, like, for videos, I'll be able to go ahead and see, like, more of.
If you can just tell me what you're not understanding about it, I'll try to explain it.
Because I know that with the acids and bases, like, it's easier to tell, like, which ones go where. So for this one, it's like, is it the
You could think of it just being outsides and insides. The
Yeah.
Pb2
Oh,
plus,
okay.
the Pb2 plus is combining with the other anion.
Okay, gotcha. So the outsides go with the outsides and the insides go with the inside.
Yeah, yeah.
Okay.
Because they're the opposite charges. You know, you're never going to get Pb2 plus combining with Na, for example, because they're both positively charged.
Okay.
But the other thing that's important is that, you know, when you're looking at the Na plus NO3 minus, you're only looking at one of each of those. You're not trying to
Do all three. Or
do
get
all of
three.
them. Yeah.
Okay.
Because that's common. A lot of people will do. They'll say, oh, that's Na2, NO3, 2, sorry, NO3, NO3, 2. But that doesn't make any sense.
Okay.
Yeah, our first priority is to figure out what the compounds are, and we can only do that once we know what the species are forming those compounds, and then we can even them out. That's where that comes into play.
Oh, okay. I think I get it now.
Okay.
Thank you.
Any other questions? All right, we can balance this. We can put a 3 in front of the PB. That means there's 6 NO3s over here now. So I need a 6 in front of the NaNO3. And that means we need a 2 in front of the Na3PO4. And that gives us 2 PO4s, which matches down here as well. So that's the balanced compound, or the balanced reaction. Now we can also add some states here. We know that's aqueous, we know that's aqueous. Now what we don't know is what the states on these are. And I had already said that when these things add together, the aqueous solutions are just going to be usually clear solutions. But when we add them together, we get a precipitate, which is going to be a solid. So one of these things is going to turn into a solid, and we need to know which one that is. So to do that, we look at the solubility chart, which will enable us to make that determination. So we look at lead and PO4, which is phosphate. So lead is here, and phosphate is over here. And when I bring them over to each other, I get I. And if you look at the legend here, I is insoluble or partially soluble. So a solid is forming here. So we know that the solid here that we're getting is Pb3PO42, the combination of lead and phosphate. The other one is going to be aqueous because it comes up with AQ as where it crosses. So that's how we know which one's solid. Now you're not going to have to worry about that. I'm actually going to tell you what solid is on the test, so you don't have to worry about using a solubility chart, but that's how you would do it. Does anybody have any questions so far? So that what we're seeing there is the predicted and balanced equation for the double displacement. So you remember that was the first task that we needed to perform, balance and predict the products of this, which we did. The next thing we need to do is write the full ionic and the net ionic equation. Now the thing with the full ionic and net ionic equation is that we split up anything that's aqueous because those already have ions split up. And we do not split solids. The reason that Pb3PO42 is a solid is because it doesn't split into ions. That's the reason it comes out as a precipitate to begin with. But anything that's in aqueous solution is present just as ions. So how do we deal with that? Well, let's have a look. With the 3 PbNO3 think of it like this. Three boxes that contain Pb2 plus and NO3 minus. The other one will be 2 boxes that contain 3 NAs and PO4 3 minus. The Pb3 PO42 we don't do anything with, it remains as a solid. And then the other one is going to be 6 boxes that contains Na plus and NO3 minus. So if we want to figure out how many of each ion we have, you can see we're going to have 3 Pb2 pluses. We'll have 6 NO3 minuses. We'll have 6 Na pluses. We'll have 2 PO4 3 minuses, which gives Pb3 PO42 solid, which doesn't get split up, plus 6 Na plus 6 NO3 minuses. Now you might be wondering, is it necessary to put the charges on? It is, because it's an ionic equation. That's what ions are, charged particles. So if I'm asking for a full ionic equation, I'm expecting to see charges. Does anybody have any questions?
So what exactly is the difference between full ionic and the net ionic? It's just,
Well, I'll get to the net in a second, but that's the full.
okay.
How do you set up a full ionic equation if you because I know this it confuses me a lot when I have to do it, so I just want to know like how you know how to set it up if you
Jacques, I'm not sure exactly what you're asking. Can you be more clear about your question, please?
I think it's like kind of how to set it up, because it tends to confuse me when I have to do it. So
Well, what confuses you about what I just did, and then we can go from there.
because it makes sense right now, but I just want to make sure I understand. So I don't know if you could go over it again, just to because I want to make sure I understand it.
Okay. So are you okay with the first part where we came up with the reaction, but had the balanced reaction with the solids and the aqueous? The part A part?
Yes.
This part? Yeah? Are you okay with that?
Yes.
All right, so part B, what you would do is you take each compound and you have to split it up into the ions that makes it up. So we've got PbNO32, which is going to be Pb2 plus, and then 2 NO3 minuses are going to be drawn with that. The Na3PO4, we have to split that up into ions, so 3 Na pluses and then 1 PO4 3 minus. The issue, though, is that we have these coefficients out the front, which tells us how many of each we actually have. So think of the PbNO32 as being in one box, but we have 3 of those boxes. So if we drew out 3 of those boxes, we'd have, let's think of this as being like an orange and 2 apples. If you had 1 orange and 2 apples, that would mean that down here we would end up having 3 oranges and 6 apples, because we have 3 boxes that each contain an orange and 2 apples.
Okay.
And we do that for each one, but we don't split apart the solid because it's a solid. The solid doesn't split apart because it's a solid. So if you just think of the anions and cations as being apples and oranges, then you can see that it's not that difficult to count them up.
Okay.
Jack, I'm not sure if I've answered your question though.
I think it cleared most of it up.
Okay. Well, I mean, if you come up with anything else while I'm doing it, let me know. Okay.
Okay, I will. Thank you.
All right. Does anybody else have any questions? Anything that might help Jacques out? Maybe you guys have got some sort of insight. Okay. So that's the full Ionic equation. The net Ionic equation, if you look at the full, you'll see that there's species that are the same on each side. You've got 6 Na pluses and 6 NO3 minuses, and that's the same on each side. So if I want the net, what I have to do is cross those out on each side. And all I would be left with is this equation, which is the net 3Pb2 plus 2 PO43 minuses gives Pb3 PO42. And that's a solid. And that's the net. I didn't want to put this on a separate page, so that's the net down here. You'll also notice that the net Ionic equation is really just what is forming the solid. If you really take it down to tin tacks, you can always tell that it's just going to be whatever makes up the solid here. So it's going to be 2 PO4s and 3 PBs. Then you just need to know the charge on each of those, and then you can come up with the net Ionic equation directly from what the solid is. Does anybody have any questions? So somebody had asked about the net. I can't remember who it was. Was it you, Joseph, who asked about the net?
Yeah, yes, it was. It was me.
Yeah. You okay with that?
Yeah, a little bit. Can you go over it one last time? Just
Okay, so once you've got the full, then you can get the net. And the net is going to be with the same things cancelled out on each side, which really ends up just being whatever is forming the solid. If we know what the solid is, we know it's Pb3PO42, I know it's going to be formed from 3 leads and 2 phosphates. If I know what the charge on the lead is, then it's just going to be 3 Pb2 plus and 2 phosphates anyway. So that's how I can get it, even if I don't know, even if I had done the full Ionic equation, I can get the net Ionic equation from that.
that's much easier to do. So thank you.
Yeah. All right, any other questions?
Okay, so I think I figured out what usually trips me up. But for the full Ionic equation, it was I think it's usually how you do the product. Because I think I can figure out the reactant, but the product usually gives me trouble.
Okay. So we're going back to how we got that from the outset. Are you okay with what joins with what, Jacques?
Yes.
Okay. So then it's a matter of making sure that the positives and the negatives even out, and also making sure you only choose one of each in order to make that determination. So the Pb2 plus is going to join with the PO43 minus. You know that one of each of those is not going to cut it because that's not going to be even. So if you take 2 and you multiply it by 3, you get 6. And that means you'll need 6 plus and 6 minus, which is how we come up with Pb3 PO42, because that will enable us to get plus 6 and minus 6. And that will balance it out. For the other one, we're just taking Na plus and NO3 minus. We join them together. That just gives NaNO3. Positive and negative will cancel. So is that okay?
I think so.
Okay. All right, let's take a look at the sample test and we'll see what kinds of questions you're going to be asked about this. It's actually not quite as bad as what I've got here, really. All right, so let's say we've got this situation and we're looking for compound A plus compound B. And here you can see that you've got all these answers here, which are going to be compound A and compound B. So let's go ahead and we'll just do this sort of piece by piece, and you'll see what I'm talking about. So this is what you would do. You take the Ca and draw a picture of it. It's going to be Ca and 2 Cls. They're going to be -1 each, and 2 plus is going to be on the Ca. Does anybody have any questions so far? Cl is -1 because it's in group 7 on the periodic table. I don't know if I have a periodic table anywhere in this module. Is everybody okay with that? Okay. And K2CO3, CO3 is -2, K is 1 plus, K is 1 plus. Any questions? So what's going to join with what? Well, the Ca will join with the CO3 2 minus. The Cl minus will join with the K plus. So I'll end up getting Ca2 plus and CO3 2 minus, which will form CaCO3, and K plus and Cl minus, which forms KCl. So those are my compounds A and B. Does anybody have any questions? Any questions? So Jacques, you said that was the problem you were usually having with this?
Yes, I think so.
I do have one question.
Yeah.
For this. Are there going to be questions where we have to type out the problem, and if so, how do we type out the charges? And
no, there won't be. No, because of that, because there's formatting issues with that. I don't tend to have those kinds of questions.
Okay, thank you.
It makes it a bit easier, actually, Joseph, when you don't have to worry about typing it out. I think it makes it too easy, to be honest, if I'm being completely honest. I think you guys get off really easy with this sample test. All right, let's look at the next part here. The sum of coefficients of the full Ionic equation. So I actually give you the balanced equation here in order for you to do that. And now you need to come up with the full Ionic equation. So here's what I would do. It's actually a little bit easier than what I was doing. You don't even really need the charges in order to answer the question. So it's like we've got one box that contains Al and 3 NO3s. Remember, 1 apple, 3 oranges, if you want to look at it that way. Then 3 boxes that contain, say, 1 banana and 1 pear. Like that. Okay, that's a 1 out in front there. It doesn't look like a 1, but anyway, it does now. And then that gives ALOH3, which again is just one of those. But that's a solid, so you just leave that the way it is. So you wouldn't even try and split that into ions. And then three boxes that contain K and NO3. I mean, I'm going to go ahead and put the charges on, but you don't really need them to answer the question. And then you can count them up. So 1, that'd be 4. This would be 6. This would be 1 because it doesn't split apart, and this would be 6. So you add all that together, that would be 17. So that's the easy way of doing it, I think. Does anybody have any questions? Any questions? Okay, by coincidence, this one's looking for the net ionic for the same thing, but I'm going to show you this one from scratch. Often you won't get the same one, but you did this time. So what I would do for the net is I would concentrate on the solid, which is AlOH3, and I'd ask myself the question, well, how would I form that? Well, it should be fairly obvious. It comes from 1 Al and 3 OH. We give that. And if we put the charges on, it would be that. So the sum of coefficients then would be 1 plus 3 plus 1, which is 5. So I think that's the easy way of doing it. Anybody got any questions? Nobody has any questions? Hard to believe.
How did you get the net ionic equation so quick?
So who was asking that? Oh, I didn't see. Didn't see who it was. Sorry. Who was asking me that?
Coden.
Okay, Coden. So the net, I looked at the solid. I concentrated on the solid. I knew that the net ionic equation is just based on what's forming the solid. So it's 1 Al and 3 OHs. That's how I come up with it. The rest of it, the K and the NO3, so they're going to end up canceling out.
Yeah. That's a lot easier than I thought. Okay.
Yeah, it is, isn't it?
Yeah.
I mean, if you wanted to, I mean, you could write out the full ionic equation on the whole thing here and then cancel out what you're not using. But if you take the step of realizing, well, look, the only thing you're going to get is what's forming the solid. I mean, this is all going to stay aqueous.
Yeah,
then,
I never realized that.
Then why worry about it?
Yeah. Huh. That's gonna help a lot. Thank you.
Yeah. It's a good thing. It's a good thing you all attended class today, hey? So you could find this stuff out. I don't know. There's a whole bunch of people who are going to say, they're going to be scratching their heads, wondering how to do this, but not you guys. All right. Does anybody have any other questions? Anybody have any other questions? Okay. All right. Let's look at the other kind of question you can get here. So this one, this is how I kind of get around the formatting. Somebody was asking me about formatting and how you would type in charges and stuff. This is kind of how I get around it. So if you've got K2SO4, I'd want you to be able to split that up and say that's K, 2Ks SO4. And we've got CrCl3, which would be 1 Cr and 3 Cls. And all we're interested in is the things that are on the ions on the reactant side of the equation. That means the ions that are on this side of the arrow. So the K+, SO4 2 minus, Cr3+, Cl-, Cl-, Cl-. So the ions are going to be K+, they're going to be SO4 2 minus, they're going to be Cr3+, and Cl-. Notice I only take one of each of them. That's why the answer is not this one here, like K2, 2+ or anything else, is because they're separate. They're separate ions. So it's K+, SO4 2 minus, Cr3+, and Cl-. So those are the answers that you'd put down. Does anybody have any questions? I mean, just to further clarify that, if you were doing the full Ionic equation, it would look like this. And what we're looking for as the answer to that previous question is just the ions themselves and not the coefficients. Does anybody have any questions? Okay. So I think it's probably a good place to stop for now. So on Monday, we'll do the single displacement and the decomposition reactions. And then on Wednesday, I think it's review. And then on the following Monday, I think the test is due. Remember, the test can be done anytime. I don't know, this time limit is concerning me. I don't think you have that kind of time limit on this test, but I'll look at it. I'll look into that. I think there might be a mistake there. I think it's 2 hours and not 4 hours you get. Okay. All right, so we'll leave it there for today. I will catch you all on Monday.
Thank you, Professor. Have a good day.
Yeah, you
Thank
too.
you.
Thank you.
See you Monday, Professor. Have a nice day.
Nice
Yeah.
day.
Bye.
If anybody wants to hang around, they can.